Okay, I think we're ready. We did intro, or well, not intro, but a whole first session on beam deflection last time. We went mainly over the theoretical approach to beam deflection, but we did end with some applications from the charts, pre-solved equations for beam deflection. We're going to pick up there, do some more, not initial, but I guess beam deflection problems. But we're not going to go back to the calculus, equation of the elastic curve. We're going to use the pre-developed equations and the concept of superposition. So that's mainly what we'll do today. It shouldn't take terribly long, and I'll try to keep an eye on the chat to make sure that there's if there's any questions. This coming Monday, should be mostly exam review type stuff. But if you have any questions today, we can go ahead and try to address some of them now. But let's go over to our page here. Let's see there, and let's just work on a couple of beam. Well, first let's go grab our equations we're going to use. So they would be over here. You could use this chart. This chart is slightly different than the one that's in the exam reference. It has a few more beam loading configurations in this chart. But we're not going to use those on the exam or the homework, so I think this chart is better in the sense that it's clearer, it's easier to see. So we're going to use this one just because the scan of it is better. But the equations and everything, it is possible that this equation, for instance, for this cantilever beam with a point load might be in a different form than the one on the exam reference, but they're the same equation, just different forms, possibly. I did not check. All right, let's get this. Let us set up some kind of beam. So why don't we start with hold on, I've got to reset something here because otherwise it's going to be difficult to write on the screen. So let's do that. I need to reset the screen so I can turn off the touch. I only want the pen to function. All right, let's see if that, there we go. All right, otherwise it gets confused and it's hard to draw. All right, so let's do a relatively straightforward one to start with. Let's do a cantilever. I would rather draw it in black ink though, so let's do that again. There's our beam, and let's do superposition. So what we're going to do is we're going to have at least two to superimpose them, loads. I'm going to put one as a point load, and this is a cantilever beam, by the way, so I've got this thing embedded in a wall somewhere. Something like that. And we'll actually use numbers this time instead of just variables. Let's say that this is a, I don't know, 5 kip. That's probably too much. Let's do 500 pounds. And then let's put a distributed load on the same beam. So I don't know if I'll go in and draw every one of the arrows on here. Maybe I will, just to make sure we understand that this is a distributed load, and it's going to be 50 pounds per foot, we'll say. And then we only need one dimension, being how long is the beam. And let's say that it is, well, let's just count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Let's say it's 14 feet. That's kind of long for a cantilever beam, but let's say that's what we have. Now we need a couple of things. If we want to calculate beam deflection, we need to know what kind of material is this beam made from, and what's its cross section. So one thing with the charts, So the charts, the beam charts that have a name W10 by 40, whatever the name might be, that 40 in that example, the weight does assume that these are steel beams. So if these beams are some other material, then that beam name would not necessarily represent their weight. If if they were made of magnesium, they're not going to be. But if they were made of magnesium, then they would have a different density and the same shape, and everything would not be that weight. So you do have to make sure that the charts you're using are for steel beams, but I mean, that's most all of the time that these beams are steel. It's very, very rare that they're going to be some other kind of beam, other material. But that is a thing to make sure that you are aware of, is that the beam name does depend on the material. So let's just assume, since based on that this is a structural steel. That's sort of a generic steel used in I-beams and things like that in a building. And we have a thing in our material properties that says the E. Oh, I might be covering this up. Let's write it over here. 29 times 10 to the 6 psi. So that's from the tables of material properties. We could go look that up. I just remember it. We also need something about the cross section. Let's just make this one a rectangle. So the cross section for this one is just going to be a rectangle, and we'll say that it is I don't really know. I've got a really long beam here with 500 pounds on the end of it, so it needs to be pretty big. Let's say it's 4 inches this way, and we'll just make this one 2 inches. And it's just a solid rectangle. And we can calculate our moment of inertia as the moment of inertia of a rectangle. If you don't remember the equation bh cubed over 12, you could go look in a moment of inertia chart, which you would have to look that up. And so for us, that would be 2 inches times 4 inches cubed. Well, 4 inches cubed, not 4 inches cubed, over 12. And that number, 4 to the third power, times 2 divided by 12, 10.7 or 67. Okay, so we have values for E and I, which are going to be in our beam deflection equation. Now we need to figure out how we're going to divide this into something that matches our list of possible scenarios here. So also we need to know what we're trying to solve for. Case 1 is cantilever beam, concentrated load P at the free end. We have that. We have the 500 pounds at the end of a free end of a beam. We also have something like case 3, cantilever beam, uniformly distributed load. It gives it a value of omega. And that says newtons per meter. That does not actually matter if it's newtons per meter. It can be foot per pound or whatever. The equation's not going to change based on the units. At least these equations. They don't have any kind of coefficients that are based on the units. So it's okay that ours is not newtons per meter. Okay, so we're going to use those two scenarios, calculate one of them, probably the point load first, and then we'll calculate the distributed load, and we will add the results together. That's superposition. So basically, if I were drawing this out, what we would do is, I'm going to copy it so I can do it quickly. We would have, let's see, maybe one scenario where it's just the point load, or I think they used a concentrated load. Don't really want to go erasing all these things, but that's what we'll do. Maybe we'll do it that way and we'll just redraw that line. There we go. So this two load scenario together, point load and distributed load, equals the point load plus, so whatever the point load does, plus the distributed load. That's superposition. So this one we'd erase, oops, put it on top of the thing, didn't I? There. This one we'd erase this guy. So if we took those two cases, which that's case 1 and case 3 in the reference sheet we're looking at, calculate whatever we want to calculate, add those results together, that would give us the same thing as these two together. That's the way superposition works. So let's just do a simple one, and let's just say we want to know the maximum deflection. So in this case, the maximum deflection is at the end of both of these beams. It doesn't actually say that here. Sometimes it specifies at the center at x equals this. In the cantilever beam, as long as these loads go all the way to the end, then the maximum deflection is at the end of the beam. It would probably be at the end even if they didn't go all the way to the end. So it's kind of assume that you know that the maximum deflection is at the end of the beam. If you didn't, you could use your equation of, well, they call it deflection at any section in terms of x. We called it the equation of the elastic curve. You could use that and just plug in the value for x, but generally the maximum deflection equation is going to be simpler. All right, so we need these two equations, PL cubed over 3EI, and that will give us, you know, this distance. Let's move this a little bit, I don't know, over there somewhere. And then we need omega L to the 4th over 8 EI. And that would give us, let's see how to draw that one. I did from the bottom. So we do need to make sure that we're adding the equations we're calculating. We need to make sure that we are adding the same point together. So it would not work to pick maybe, you know, this point on the point load version and this point on the omega and add those together. They do need to be lined up, same x coordinate basically. So we do need to make sure we do that. If we wanted to, another way we could approach this is we could take the equations for the elastic curves and literally add them together. So px squared over 6EI times the quantity 3L minus x plus omega x squared 24EI times that quantity. So we could do that if we wanted to and make one giant equation as a function of x and just plug in the value. If you were using MathCAD or something where it was easy to deal with large equations like that, then that might be an easy way to do it. So since we're doing it by hand, we're going to be a little more manual, and I'm going to say that our goal was to find the total maximum deflection. Maybe we'll write that down. So what we're trying to do is find max delta. So maybe that's what we're trying to do. And we know that maximum delta is at x equals 14 feet. This time I'm measuring from the wall. Last time, just for the sake of developing the equations, we did measure x equals 0 was at the free end of our beam. That was really only for trying to figure out those theoretical equations. most of the time X is going to be 0 at the wall. You do have to check that with, your picture here. It doesn't really tell you that anywhere. You can pick up that the X-axis is here, and you can kind of assume, oh, here it is. You can see the Y-axis is at the wall, and that would be where the Y intercepts the X. That's your origin. So it is built into these pictures. All right, so let's just do the math and see what we get. So for this one, for the cantilever, PL cubed over 3EI, P's 500 pounds, L is 14 feet. Now I do have to be careful. E is going to have pounds per square inch in it. I look at it right here, it's inches to the fourth, and I've got feet in the numerator, so that's going to be a little mismatch. So I'm going to convert it over to inches, and I need to cube that. 3E is 29 million. I just told you that, but you would need to go look that in a chart somewhere. And I we calculated because we said the cross section was a rectangle right here. So if we can get all of that into our calculator, trying to plug it all in, I think it ends up a relatively large number, 2.55 inches. I'm not terribly surprised. That is a large number for deflection, but I'm not terribly surprised because our beam is not that large, 4 by 2, and it's 14 feet long with 500 pounds on the end of it. That seems like it probably would deflect that much. Now, one thing that these equations don't do is they don't consider the beam twisting, or like if you really tried to push a 14-foot long beam, it probably wouldn't nicely deflect like the curve, the green curve that I've drawn. It probably would want to twist out of plane and all that. These equations don't consider that at all. They assume it stays perfectly in plane. Let's just see what the 50 pound per foot distributed load does. So 50 pounds per foot, same deal. I've got feet here versus inches, so and one thing that I see when you get in a hurry on one of these, you're trying to crunch through all the numbers. One thing I see that happens often with the distributed load is instead of dividing by 12, you accidentally multiply by 12 like you did up here when we converted these 14 feet. So be careful with that. L is 14 feet. This one we need to, this is why I write out the, the conversion factor. So 14, but it needs to be raised to the 4th power. And then a little bit different denominator, 8 times the 29 million. Same moment of inertia, which I forgot, 10.67. Okay, let's see. I should have saved my denominator, but I didn't. Oh, it's different anyway. Okay, let's see. 14 times 12 raised to the 4th power times 50 divided by 12. all of that divided by our denominator, I get a reasonable number, 1.34 inches. So these two together do kind of make me think that we're on the right track. They're large-ish numbers, you know, several inches, but this is a really long, skinny beam, so it really probably would deflect some, maybe even under its own weight. But what our actual answer would be, delta max would end up equaling 2.55 inches plus 1.34 inches. Again, assuming that everything stayed in plane and it just bent kind of downwards, which it may not do in real life. 3.89 inches. I kind of think in real life it would want to twist a little bit and go out of plane and do some weird stuff. But that's how we would calculate. That's how we would use superposition to calculate that. So this is kind of probably the most basic version. The ones we did yesterday were actually a little more complicated than this, but they weren't really superposition. They were more like substitution, I guess. We had a point load, and we converted that point load over to a concentrated moment in order to calculate some things. Let's do one. Let's just do some of the common-ish examples so you can see that there are other ways this stuff works too. Let's say, and I know I'm focusing on cantilever beams, but last time we did a simply supported beam as our example, so we're doing some cantilever beams this time. Let's do one that looks pretty simple, but it's different. So here, let's just use the same numbers we've been using, so that we don't have to deal with the moments of inertia and modulus of elasticity E. So we can just keep those numbers. Let's keep that. Let's just change up the load here. I actually don't know if I made the beam the same length or not. 1, 2, 3, 4, 5, 6, 7. I did not. Let's actually make this 8. And this one 6. Just so we have the same length beam. Those would be feet. Okay. So this one's a little different. The point load's not all the way at the end of the beam. So how we treat this is we did a similar-ish thing yesterday, but not quite the same. So this little section of the beam is actually not bending, unless it's bending under its own weight, but we are ignoring self-weight for now. So what this beam would do would look something like this. So it would, and I'm exaggerating, bend, you know, flex, bend, let me make it more curved. Okay, that's more, clearly that's curved, like it's bending. But the pink part of the beam would just be a straight line. Okay? Again, way exaggerated, but that's what we consider. We sort of did that last time, it just in a different way, where there was a concentrated moment. Actually, there was a point load that we converted to a concentrated moment, which was twisting the beam, and then the beam started out at a twisted angle or a sloped angle, and then it bent from there because there was a point load on it. But this is how we would deal with this one. So we can calculate this angle theta because we have case 1 tells us theta, and it shows theta being the angle of slope at the very end of the beam. I don't have, at least in this chart, I don't have an equation that's giving me theta as a function of x. If I needed that, I'd have to go back to the theoretical approach that we used last time, or find a chart that did have that in there. Most charts don't have that though. So PL squared over 2EI here's the thing that trips up some people though on this one. They look at PL squared over 2EI. P is fine, it's obvious 500 pounds. EI we've already got. 2 is just 2. L is not 14 feet. L, look at our picture. L is the distance from the wall or the fixed support to the point load. That's only 8 feet. So that is a thing to be aware of. L in this equation is only 8 feet, not 14. So you do have to match up the diagram that comes with your equation to your scenario that you might be dealing with. So don't look at like L is the length of the beam. Look at L in relation to where the loads are. Okay, this distance that is the deflection at the end, well, not at the end of the beam, the deflection underneath the point load. So that's actually the equation we just used, PL cubed over 3EI. Same thing here with L though. That L is the distance from the support, the wall, to the point load, not all the way out to the pink part of the beam. So how do we calculate the rest of our deflection if we want to find, again, I guess I should write down, find max delta max. That's what we're trying to do. So that would be the deflection at the very end of the beam. So we need the rest of this deflection. We need this distance. It's going to be kind of cluttery there. That part is going to equal, and it's another one of those, we're going to cheat a little bit. You could use a triangle. You know, we have theta there. We have a right angle triangle, and so we could use a calculation like that. But what we normally do, since these are generally small deflections, we can just say that this is essentially just the arc length. And in this case, R is the length of the part that's, you know, tilting down. So it's the length of the pink section, 6 feet. Okay, so with all of that, let's calculate what our delta max should be. So the first little section, we can call that delta 1, I guess. Delta 1 equals PL cubed over 3EI, 500 pounds, times 8 feet, but we got to convert 12 inches per foot, cubed over 3. We haven't changed our material, and we haven't changed our beam. All right, fine. So if I can plug all that in and put it in my calculator. Whoops, that's not the right number. Just trying to get all the stuff in there. Nope. I didn't do it all. Hold on. Got to do it again. 10.67 times 29 million times 3. That's my denominator. 8 times 12 raised to the third power times 500 divided by my denominator is 0477. Okay. That's only that's just this amount of deflection though. We need to add in this amount of deflection. So that amount we decided is going to be this arc length over here. So we're just going to take theta, PL squared over 2EI, and multiply that by R, where R is 6 feet. And we'll just call this one delta 2. That's Q squared though, squared over almost the same denominator, but it's 2 instead of 3. And we can't forget to multiply by R, which I've got as 6 feet, with deflection. All right, let's see, 10.67 times 29 million times 2, that's our denominator, time, or well, 8 times 12 to convert feet to inches, squared, times 500 times 6 times 12 divided by our denominator, 0.536. So that would be delta 2, just the distance that the pink part has kind of, it hasn't bent, it's just tilted down that far. And it's tilted by the amount of that angle theta that we calculated, which we did that with that part of the equation. All right, so our total max deflection would be 0.477 inches plus 0.536 inches, so about an inch. Let's see. Oh wait, I did multiply, sorry. Plus 1.013. Why do we make L2 8 instead of 6 feet? Let's see, L2, oh, L squared, I guess is what you meant. I assume you mean that number, because this equation, PL squared over 2EI, that's calculating the angle theta here. And that angle theta is really, I've drawn it kind of in the pink section, but it's really the slope of the end of the beam. So theta is really the slope at the end of the beam. You can kind of pick that up from our deal here. It's kind of small though. Maybe if I get this little guy. So there is their line, that's their tangent line. The equation's right there, PL squared over 2EI. So this equation here at the top of this picture is referring to the diagram right next to it. Let's see if I can get my camera to back do something again. There we go. So that's why it's the 8 feet. And your other part of the question, if we flip the axes, no, I would not flip the axes, because that would change these whole equation sets. These equation sets, let me go back to here. These equation sets have an axis built into them. You know, there's X, and here is Y. And so that means that since Y crosses at the wall right there, that's where X equals 0. So if we flipped it like we did the other day when we developed our equation, that would change all of their equations too. So if you flipped them, all of these equations that they have developed would all be messed up. So I would not flip the axes. that's the short answer of that one, is I just wouldn't do that. All right. So this one's not really superposition exactly. It's only one beam case number one. But it is something that is pretty common, where you can take an existing case and use it in a scenario where it's not quite the same. It's similar, but not quite the same. You just have to figure out how to account for the differences. In here, the difference was that the point load wasn't all the way at the end of the beam. You know, it wasn't over here. Whoops. Here we go. It wasn't at the end of the beam. But we calculated as if this little, maybe I should color it, this little part was the whole beam. We calculated like the green section was the whole beam. And then we realized that, well, the pink section is sort of just continuing where the green one left off at. And so we are making a little bit of assumption, but it's a pretty good assumption that the pink section starts out at some angle because it's attached to the end of the green cantilever beam with the point load at the end of the green beam. It's just attached to the end of that, and it just carries on at that same angle. And so so this delta 2 is oh yeah, I saw a question about degrees. The delta 2 is just really trig, is all we're really doing. No, you will not be given something, one of these beam deflections where the y-axis is in the middle of the beam. I think there is a webwork problem where it's, I'll look and see. I think there's a webwork problem where it's not at the end. And so that requires some thinking. I'll look through them and see. Is theta calculated? Yes, it's radians. So theta, any of the thetas that we get here are radians. So this value, if we didn't calculate it by itself, but if we did that number, that would be radians. Let me show you another example of a different way that you might take some common things and combine them together. Again, with a cantilever beam. I'm showing you these on cantilever beams, but these same approaches can work. Same type of ideas, I guess, can work with the simply supported beams, but it's usually a simply supported beam with a cantilevered section, like we did yesterday. And so you kind of end up treating it like a cantilever anyway, or at least that section of it. So here's our beam. And we're going to do cantilever. I didn't really want a arrowhead on it. Let's do distributed loads this time. And let's do, so we could do a distributed load kind of like we did here, where it's the distributed load starts at the wall and ends somewhere before it gets to the end of the beam. That would be the exact same process as this one. You would just use the equations for distributed loads. But what if this was what it did? So what if your distributed load was over here? Your first thought is probably close, but it's probably not right. At least not, there's a better way to approach it. So your first thought, let me make sure that we know that these, actually this is going to matter in this one. Your first thought is probably, oh, well, I will just lump the distributed load into a point load and put it right here, and that'll give me the same effect. And it's close. It's like really close. And so if you were doing, you know, just a first pass or whatever, then it's probably good enough. But there's actually not quite the right way, because if you treated this as a point load, then basically you've got the same exact problem you had right here. where there's a little pink section that is not bending, it's just at some angle. But there is, there is a force, distributed load on that pink section, so even though it's not much, it is actually continuing to bend, not just follow some angle. So although it would get you close, that's not the best way to do this one. The best way to do this one is actually a little bit weird, but what you would do is this would equal, I think I'll just draw it off to the side here kind of small, because otherwise it takes up a, well, no, let's do it up and above like this. There we go. So why don't we copy it? All right, so we'll need one of these here. Put it maybe there. And we'll need another one. We'll put it right there. All right, so this equals, let's get rid of this. We want to relate it back to cases that we actually have equations for. So we don't have an equation where there's a cantilever beam or a cantilever beam with a distributed load on the end of it. So we do have cantilever beam with a distributed load starting at the wall and going all the way to the length of it. I think that's case 3. But what we actually want only has the distributed load at the far end, and it doesn't make it all the way to the wall. So what we actually need to do is we need to somehow eliminate this part of the distributed load that touches the wall. So what you do is, I'm going to draw it underneath here. You could think about it this way, or you could do a subtraction. You could think about it as adding a distributed load that's pushing the beam back upwards to counteract all of this section. These two would basically counteract each other, and they would leave you with only the part of the distributed load that is at the end of the beam. Or you could say, instead of a add, I did a plus sign, you could do minus, and then you could put the distributed load on top like you normally would. Why you can do these is because we have this case 3 here, where there's a distributed load that starts at the support, the wall, and goes to the end of the beam. So that's exactly my middle one here. And then this one, well, it starts at the wall. It doesn't go all the way out to the end. It doesn't cover this part. But that problem, that third diagram there, is the exact same thing as this. It's just, instead of a point load somewhere near the end of the beam but not at the end, I've got a distributed load. So I could calculate these two, and that would give me the exact same effect as the distributed load off to one edge at the end of the beam, whereas doing the lumped version here, that does not give me the exact same effect for that section out at the very end of the beam. So that one's probably doesn't show up as much, but I wanted to show you that just because it's not always that you have to add them together. Sometimes you can subtract them, or in this case add a negative version to counteract one. That might be a way to approach it. Let's talk a little bit more about the one we did last time, because there is a little piece to it that I didn't really say, but we used, I guess. So last time we had, let's make it the right color. Last time we had something like this, but it was a simply supported beam, and one of the supports was somewhere in there. Something like that. And we had a point load over here. So what we did with that one was we don't have, none of our equations for simply supported beams give us a piece of the beam that's cantilevered. So we don't have that. But we do have this case number 9 with a concentrated moment. So what we did is we said, well, that's equal to, whoops. That's equal to this. Instead of a point load at the end, we said that, well, we can do this. And get some of the same effect. The problem with this, and it worked for what we were trying to solve, is that this only works in this part of the beam. So that only works for here. So these are not actually equal for the whole length of the beam, because same reason that we've been encountering here, and we solved it the correct way when we did the example, but I don't know if I explained why we did that or not. So if we look at the bottom picture, oh, well, let's look at the top one. The top one, if we were drawing its curved shape, you know, it's going to do something like that, right? And if we did the same thing for the bottom picture, it's going to do something like that. Okay, so I should have drawn those exactly the same. In the pink section, they would be the exact same. Looks like I drew my bottom one more deflected, but the difference is going to be in here versus here. So in the point load version, this segment is curved. In the concentrated moment section, that same segment is straight. So you have to be careful. That's why when we solved it last time, we had to we had to do this. We had to convert the point load over to a concentrated moment, and they did want us to find the deflection out at the end out here, but we couldn't just go and use the delta equations for the case number 9. We couldn't use those. We said that again, oh, there's some angle that this section is tilted, and then we went and put that point load on it to figure out, you know, basically how much did that point load make that part curve. These, you know, the dotted line should match exactly my green line at the top, but it didn't. So sometimes part of what you do to translate a load or to convert it over to something one of our cases matches with doesn't take the whole beam into account. So you do have to try and visualize what is the beam doing as far as, and how can I create that same effect with the equations here that I do have. Let's go through web work. I think it's homework 17 is the beam deflection. Oh, hold up. Let me... Okay. There wasn't a problem. I thought there was a problem. All right. So let's look through these and just talk through. That one is really really straightforward. The only, I guess, tricky part here is recognizing that the only load on it is a distributed load described by the 30 here. So that's the only part. It's 30. I don't know if S178, that sounds like a metric one. And the metric beam charts are, I have had a couple of questions about this. If you go to home in Canvas, which it's being slow about doing. And you look through these, C and S and W, those are only the US units. If you need the metric ones, you have to go to one of the exam references. And they're smaller in here, or the book. Look in the book. They're straight out of the book. But let's see, this is what I wanted to find. Here, down, I know it's super tiny. Maybe if I grab this little part, we can look at it. So for the metric ones, what it's saying down at the bottom of the beam here is that the mass is kilograms per meter. So be careful, don't use kilograms. You need to convert that over to newtons. So multiply by 9.8, or I don't know if this web work is using 9.81, possibly. It might say, let's see. It does not say if you need 9.8 or 9.81. Sometimes WebWork doesn't care which one you use, but it might. Could you do 15.5? We can look at it. Let's see. We'll look at that in a second. Let's talk through these, and then we'll look at 15.5. We did that one. So this one is a combination of a lot of the things we've been doing. One thing about this one, though, so usually your, let's see, where are they? Here they are. Case 5 here is your off-centered point load for a simply supported beam. You have one where the point load's in the middle, but you usually have another case where it's off-centered. You do have to be careful with the equations, because the equations only work in one region. So first of all, B is less than A. So for this diagram, the B dimension is the smaller one. It's not the one on the right hand side, it's the smaller one. So in our web work, it would be, at least looking at this picture, yes, it's I. Even though it's on the left hand side, I is smaller than J in this diagram. So be careful with some of these, particularly this one with the off-center load, because these dimensions, these variables, are set up in a way that it's not left and right. It is B is the smaller one. Also, this equation, it tells you it's only good between 0 and A. So it's only good for this larger section of the beam, not that section over there from where B is. So be careful with that problem, because it's got the smaller dimension on the left-hand side of the load. That one's a combination of what we've been doing. You've got this cantilevered section that you have to assume just tilts upwards. There's no loads out here. This one does not. Oh, yeah, it specifically tells us to neglect self-weight. So there's no load out here on section CD. It just tilts upwards. That one's got a lot of. This is the one I was thinking of where the origin is not at the end of the beam. So the origin's at B here. So basically AB is a little cantilever section of its own, and you kind of have to mirror the charts here, where P is off to the left. So sometimes you have to use the mirror image of the pictures in the chart to match up with what you actually have here. So just be careful that what you're actually doing is matching the diagram the way the diagram is meant to be used. Like, for instance, this one where B is the smaller dimension, not the dimension on the right-hand side. Let's look at that 15.5 and see what it says. Would we use 30 or the actual specific weight? Oh, okay. Would we use 30 or the actual specific weight? I think you mean maybe when we were using the kilograms. Maybe, I don't know. 30. I'm not sure what the 30. When you're talking about like the beam name, 30 No, it's 30 kilograms per meter. So you would use 30 times 9.8 or 30 times 9.81 to get the newtons. Let's see, 15.5. Let's see what this is about. Okay. Yeah. This one, so it's not a hard problem. It's a tedious problem. So I might can remember how to do it, and I might not can. I don't know. We'll look at it and see. So this one is if this thing had any other cross section, not this pie-shaped thing, then it's really straightforward. Not a big deal at all. It's the cross section on this one that gives you most of the trouble on this one. So let's see if we can get the moment of inertia for the little cross section, then we probably have solved all of your issues. So let's see if we can do that. I don't know if I can remember all of it or not, but we'll see. Let's just copy this whole thing. All right. So for my set of numbers, I've lost my pen. There it is. All right. I think you're probably fine with finding the reactions at the wall, RA and MA. I think that's probably okay because it's just a point load and a concentrated moment. So it's not a complicated loading scenario. I'm pretty sure this is the problem for this particular thing. So let's start with that. And then if we need some more, we can do some more. Let's start trying to find the moment of inertia of this weird cross-section. Let's read what it says. Cross-section shaped as the sector of a circle. Okay, so it is part of a circle, but it's some little wedge. We've got some force and a moment, and then we've got some dimensions. So let's draw a little bit larger version of our sector. Okay. Let's see. What are my dimensions? D, the entire height, is 24 millimeters. What else do we know? C, kind of the width of this sector is 23 millimeters. So we'll put that down here, I guess. Okay. First, we need to find where's the neutral axis, right? So I don't know the neutral axis of a sector of a circle, so we're going to have to look up our chart. I think it's power to the 4th over 4, maybe, but I don't know. Let's see. Oh, that might be in here. Let's see. There's our beam deflections. No centroids in that one. There it is right there. All right, so let's grab this little guy. And go back over here. A little bit crooked, but I think we'll be all right to deal with that. So it's rotated, you know, from where we are. If we were to rotate it, you know, that's more like what we have. So according to that, what we want is this thing called, that they're calling x sub c. That would be the distance from some kind of central axis here. You know, maybe that's... And it measures from the point up to the centroid. Centroid looks like it's supposed to be somewhere in there. So that's what distance we want to find first. And they tell us that that is, oh, it's weird, 2r sine alpha over 3 alpha. Okay. So that distance is 2 times r sine alpha over 3 alpha. And they say that alpha, it's right in here, it's half of our angle. So this is alpha. Okay. Let's see. I think we can get alpha because this would also be alpha. Alternate interior angle, whatever you call it. That's alpha. And we have those no, we don't have those dimensions, but we have the radius. It doesn't look like we have the radius, but we have the radius is 24 millimeters, right? That distance is 24 millimeters. And we have half of 23. Whoops. Is this distance. Okay, so I can get, what's that? The sine of alpha is the opposite side over the hypotenuse, right? And I'm thinking of this as a triangle. Thinking of that triangle. Okay, so sine of alpha equals opposite side over the hypotenuse. So 11.5 divided by 24, 0.4792. That's the sine of alpha. So the inverse sine, I'm in degree mode though, so we'll have to deal with that. Where do I do that? Sine of 0.4792 is, so alpha is 28.63, but that's degrees. These equations, this equation over here, that equation, those are radians. So particularly you can see the 3 times alpha, that alpha has to be radians. I guess you could put sine of degrees in there if you're in degree mode. So there could be a problem with just getting this part because you might be mixing up in your calculator using degrees and it needs radians, or there could be something like that. So actually we know the sine of alpha. This is the sine of alpha right here. So that part of the equation is already solved for us. But we need the actual radian value. So to convert to radians, we multiply by pi, divide by 180 degrees. So 28.63 times pi divided by 180 is 0.4997 radians. Okay? Why is 24 the hypotenuse? Well, 24 is the radius. So my picture's not great, so that's one part. You know, I don't have the arc that I drew is not a perfect circle. Maybe I could do that. I wonder if I can get a really good circle on there that's the right size. Maybe. So that would be the actual shape here. Kind of covered up some of the stuff I didn't want to cover up, but so there's the actual shape for the at least for the arc that I drew. And they told me right here in the picture, in the diagram of the sector, that the total height, this dimension, is 24 for me. They labeled it as D in the picture, and D for me was 24. And so this little line is the radius, but so is this little line. That's also a radius. So they're the same length. So they're both 24. So that's how I knew it was 24. Just fixing my drawing there. All right, so that's how I know it, that the hypotenuse for, and I'm looking at this version of alpha, right? Because I'm thinking of that triangle. Okay, so we have everything, I think, to be able to plug into the 2r sine alpha over 3 alpha. So that would be 2 times the radius, which is 24 millimeters, times the sine of alpha, which we have right over here. We just solved it, 0.4792. I'll probably need to move this somewhere. So let's just put it down here. 2 times, or this is x, well, in our version it's going to be y sub c. We had to rotate the little chart that we had. We had to rotate it so that what they have as x sub c is in our y direction. So I'm going to call this y sub c. 2r times sine alpha over 3 times alpha, 2 times the radius, times sine of alpha is 0.4792. I have that from where we calculated it up there. Over 3 times alpha in radians. So this alpha needs to be in radians. And that's what we did, the multiply by pi over 180. So that number is 2 times 24 millimeters times 0.4792 divided by 3 and 0.4997. 15.34 millimeters. That seems reasonable. You know, based on the scale of everything, that seems like a reasonable number. So that's where our neutral axis is. It won't let me. That's fine. Going through the centroid. Now, we need the moment of inertia for this shape. So let's see if we can find an equation for moment of inertia for this thing. That's the centroids. Oh, not that. Let's see. Where is our actual... There they are. Okay. There it is. All right. So, looks pretty complicated, but let's grab this guy. Maybe enlarge it a little bit. All right, so again, we've got the same issue. Can I not copy from here? Oh. Where this is not the same orientation as what I have in my picture. So I'm going to rotate it for us. That's what I have. It looks kind of weird, but that's what I have. Matching up our orientation for the sector. All right, so what it looks like, I need the moment of inertia. This gives me x sub c, so I've already got that. I need the moment of inertia about the centroid, which is just going to be I actually don't have the moment of inertia of the centroid here. I have the moment of inertia about the y-axis, which there's the y-axis down there. And that would match up with this equation. So I believe what I'm going to have to do, for some reason, this one, and I don't really remember, maybe it's because of the orientation of the sector, the XIX does go through the centroid, but IY does not. So I think I need to calculate IY, this R to the fourth mess, and then translate that up to the centroid, I think. We'll see if that works or not. Oh, you know what? I bet I don't. I bet I need to undo the moment of inertia. All right, so this is going to be a little tricky. All right, so I want IY because that's the moment of inertia about the y-axis. So let's get that part. R to the fourth over 4 times theta, which is alpha in my other one, so I will put alpha in here. Plus 1/2 sine of 2 alpha. Okay, that's the moment of inertia about the point of my sector. So normally the moment of inertia is given to you about the centroid. So that means that this one has had the parallel axis theorem applied to it. So I need to undo the parallel axis theorem. So instead of, normally it's I equals the original moment of inertia about the centroid plus AY squared. I need to undo that by subtracting, so I'm undoing the parallel axis theorem. A, which they gave me conveniently, which they have theta, I'm going to use alpha, times R squared is the area. And then Y squared is going to be the distance X sub C, which we got, we called it Y sub C because we rotated things 90 degrees. You might have to watch this one several times to get it straight. I might have to do it several times to get it straight. All right. So I think this will give us the moment of inertia in terms of our sector. So let's plug the numbers in. So our radius is 24. We're pretty confident on that. I'm going to leave the units off just because there's a bunch of numbers in here anyway, and the only numbers are millimeters. The only units. So that's to the fourth over 4. Alpha is the radian version. So that's 4997. Plus 1/2 the sine of 2 alpha. Now, if my calculator is currently in degree mode, so I'm going to use the degree version here, 28.63. And I'm going to be sure to mark down that that's degrees, because it will matter. Like if you flipped your calculator over to radians to do this other stuff, you just got to make sure you're doing the right, when you're doing the sines and inverse sines, that you're in the right mode. Minus alpha. This alpha needs to be radians, so I'm going to go back to the 0.4997 radian version, times my radius, 24 millimeters. That is just the R squared, not the theta R, or alpha R. And then Y sub C, I think we calculated that, 15.34 millimeters squared. Okay, so all of our units are millimeters. I've got radians where they need to be, so this one's radians, this one's degrees, that one's radians. I think if we plug all these things in, we can calculate the moment of inertia about the centroid, which is what we want. Well, the problem said moment of inertia about the neutral axis, NA right here, right there. And so that's the centroid. Okay, let's see if we can get this to work. All right, I'm going to start inside here. 28.63 times 2. I'm going to take the sine of that. Multiply or divide by 2. Add on the radian version of my alpha. You know, it's showing theta on this one, but I'm pretty sure it wants radians, because it wouldn't make sense to have it in degrees here. So I've added on the 4997. Still inside that large parentheses. Let's divide by 4. Multiply by 24 to the 4th. All right, so the first term here, 76330.6, those would be millimeters to the 4th. But I've got to subtract off. Remember, here I'm undoing the parallel axis theorem. Because they gave me IY as the moment of inertia about the y-axis, and they put the y-axis at the point, not at the centroid, not at the centroid of the sector. So I've got to undo the parallel axis theorem to get back to what it must have been at the centroid, where I want it. So minus, let's see what this number is, 15.34 squared times 24 squared. Oh wait, I did plus. Hold up, that should be times 0.4997. Okay, so I'm going to subtract off most of it, 67,730.23 millimeters to the 4th. Here I've got, you know, millimeters squared with the 24 and millimeters squared with the 15, and so millimeters to the 4th total. 76330.6 minus 67730.23. Supposedly, the moment of inertia about the neutral axis for this sector is, for me, 8600.37 millimeters to the 4th. Let's see if we're anywhere near the right thing. Let's just put them in. What was it? 8600.37. We do use units, so millimeters to the 4th. We will show the correct answers because I don't know. You didn't like that. All right, so I rounded enough that it didn't like that. So what it really wanted was 8579. That's a little further off than I would like. But I did round a good bit, and we're talking about millimeters. So I rounded the 4997, I rounded the 28.63, I rounded the 15.34. I think it's just a rounding error. I don't think there is an actual error. I think it's just rounding. Also calculating the 15.34, I rounded that 479, there's the 499 again. I think it's just rounding. I rounded, you know, to get into those numbers. Rounded the 28.63 when I used it. So I think the problem is rounding. For 2 alpha, could the alpha not be in radians? For 2 alpha. I put it, well, so that would depend on your mode for your calculator. So my calculator is in degree mode. So in order for me to calculate that number, I need to put it in degrees or change my calculator to radian mode. So that's why I put the 28.63 here in the 2 alpha part. That's why I put it in degrees for me. It would depend on how you're going to calculate that. We could, I think we could do, I don't know if we could do twice of that, but that's why I put it in there as degrees. It was because of my calculator mode. Yes, I am in degree mode. I'm just going to run through it and make sure I didn't. I could have also made some little error, but I don't think we'd be that close if I made an actual error. Yeah, I think it's my rounding. I carried every decimal and I got the right answer. Okay, good. So somebody did the whole thing with no rounding, as you should for web work, and got the right answer. On exams and things like that, there's a tolerance built in that's wider than the tolerance for web work. Web work has a very tight tolerance. Yeah, you stored values in your calculator, so that would be better. I did not do that on this one. I was just you saw what I did. I did this. So my difference is because I didn't store all the values, and there are, I wasn't thinking ahead that there are quite a few places where rounding is going to show up, and you square, like this one is squared, so that's going to make your rounding even worse. So there's a little bit of issues there if you don't carry enough decimals. At least as far as web work. Web work has issues. All right, so that's how you can get through that one. That one is definitely beyond what a test question would be, but it does demonstrate a lot of the different things. I'm pretty sure you're not going to have any other, in this course anyway, situations where you've got to do this part about undoing the parallel axis theorem. That's a hard one to know that you need to do. How I knew I needed to do that is because when they gave me this equation, this equation for IY, and you look at where the y-axis is, the y-axis isn't through the centroid, and I need the centroid moment of inertia, not this y-axis moment of inertia thing. And so I knew that I needed to undo the parallel axis theorem. So this equation was generated by taking the moment of inertia about the centroid and applying the parallel axis theorem to it, which means adding ay squared. So all I did is I took this equation and subtracted ay squared to get back to the neutral axis. So that's something that, if you figured that out, great. But that's a hard one to know that's how that's working. Plus dealing with the radians when you need radians and the degrees and all that. This is a tricky one. Way more tricky than a test question would be, even though the problem itself is really quite simple if you just knew the moment of inertia of this sector. All right. Let's see. I don't see any other things popping up. Be ready on Monday for whatever test questions you want to, work through or have questions about. If I see any pop up here, we'll look at those. But we're close on time. We've been at it for a while here. For the beam deflection, obviously, this kind of stuff, I think on the exams, maybe something of this level is probably the more complicated beam deflection. I would think the beam deflection is going to be, something pretty straightforward, or something that's got one of these situations where you have to use the pink region here, just sloping and not flexing. Maybe something like that. You've got some web work problems that work through these. Maybe I didn't see any in the optional ones, but maybe there are some there. I don't remember looking. All right. Haven't seen any new questions. Monday was basically question and answer. I don't even think I'm covering a new topic on Monday. And then I think we've got the exam set up for next Thursday, a week from today, and it'll follow the same format as last time. We'll have a noon offering and a 7 o'clock offering. You attend whichever one you can, not both, and get on Zoom. I'll give you a Zoom link, and we'll have an hour and 50 minutes for the exam. If you have extended time, that'll be built in also. All right, I will see y'all Monday with